one of the most useful things about matrices is that they can be used to solve systems of equations. We looked at solving systems of equations using algebraic techniques as well as graphing and looking at tables. Now we're going to look at another way to solve them, and they are going to require us to use matrices. You're going to have to know how to find some inverses to do this as well. So let's say we have matrix A, and it is multiplied by some matrix X, and when you do that, you get matrix B. Now, normally you would think, oh, I divide both sides by A, and that will tell me what X is. But remember, we can't divide by matrices. So we have to show another way of showing 1 over A. So remember, 1 over A is the same as saying A to the negative 1 power. So that's the inverse of A. So what we're going to be doing is looking at how we can use that inverse, the multiplicative inverse, in order to solve AX equals B. So if we're using the multiplicative inverse, what we're doing is we're going to multiply both sides by the inverse of A. Now A times the inverse of A is just the identity matrix, so we know that that's just 1. And what we're left with is X equals the inverse of A times B. And that will tell us what our unknown matrix, or our X, equals. And so we're going to look at how to set these matrices up using systems in order to get them in a form that we can solve and therefore find all the variables in one fell swoop. So here we have a linear system with 2 variables in it. And in order to change this into matrices, we're going to need to make 3 matrices. We're going to have one matrix, which is the coefficient matrix. And we are going to have another matrix that is the variable matrix. And this is all going to equal a third matrix, which is the result matrix, or constant matrix. Sometimes that's what I call it. So let's see how we can convert this into a matrix equation. So the coefficient matrix is just like it sounds, the coefficients of the variables. We have 4, -1, -6, and 3. Now the variable matrix. Think about how you multiply matrices. You do row 1 times column 1. So the 4 would get multiplied with the first entry in this matrix, so that needs to be X. And then we have row 2, column 1, and we want to think about what is going to get multiplied with that second part, and that is the Y. So if you carried out the matrix multiplication, you'd see you'd end up with that first half of the system. Now for the resultant matrix, well, it's just going to be 29 and -39. Think about what you know about multiplying matrices. This is a 2 by 2 matrix. This is a 2 by 1 matrix. So when you multiply them, you know you're going to have a 2 by 1 matrix as the result. And so we were able to turn that into a system using matrices. Now another way that you might see this written is you might see it written as the coefficient matrix times some unknown matrix X, which equals the resulting matrix. It's really the same thing. When you find that unknown matrix X, what's going to happen is you'll have a matrix that's a 2 by 1 matrix, and then you would apply those variables as they, in the order they come in. So how are we going to actually solve this? Remember, what we're going to have to do is multiply by the inverse of this first matrix with both sides. That matrix is going to go there, since we multiply on the left side, and we're going to multiply on the left side again. So we need to find the inverse of the matrix. That's our first step. So our first step is finding the inverse of the coefficient matrix. So remember that the inverse is 1 over the determinant of A times the mixed up matrix. So the mixed up matrix is flip those two, and these two switch signs. So the determinant of our coefficient matrix can be found by doing 4 times 3 minus negative 6 times negative 1. So it is 6. So when we're finding the inverse, what we're going to have to do is 1 over 6 times 3164. Alright, so let's go ahead and do that. And that gets us 1/2, 1/6, 1, and 4/6, which is 2/3. So now that we have A inverse, we can do A inverse B, or A inverse times the resulting matrix. So that's going to look like 1/2, 1/6, 1 and 2/3 times 29 and negative 39. So this is a 2 by 2 matrix, and this is a 2 by 1 matrix, and we know our resultant is going to be another 2 by 1 matrix, which makes sense because we're trying to find two variables here. We're trying to find x and we're trying to find y. So let's go ahead and carry out our multiplication. Row 1, column 1. So we are going to end up with 29 halves minus 39 sixths. And then I'll figure out what that is in a second. I'm going to go ahead and do my next multiplication step. Row 2, column 1. So that second term is going to be 29 minus 39 times 2/3, which is 78, negative 78 over 3. So then you just need to combine these two terms, and they're going to get you your two missing variables. And in this case, what we're going to end up with is 8 and 3. All I did was add those, subtract those with a calculator. And so this way you know that at the end of the day, you were able to solve that matrix. You know that the variable x is 8, and you know that the variable y is 3. So we needed to, apply our inverses and our multiplying. So we're sort of putting everything together to solve this system. Some of you guys may be thinking, oh, my algebraic method is way easier than that. Yeah, a lot of times it is for small matrices like this. But we're going to look at some examples where they're a little bit bigger, and so sometimes using this matrix technique is a little faster. So here's another system with two variables in it, and I'm going to set up my matrices again. We're going to have the coefficient matrix times the variable matrix. And we know that when we carry out this multiplication, we're going to end up with the constant matrix. So this is the representation of that system using matrices. Now we know we're going to have to find the inverse of A, or the inverse of the coefficient matrix. And that way we can multiply it by B. So if we're going to find the inverse of A, we need to know the determinant. So to find the determinant, we're going to multiply these two guys. So we get 10 minus 15, which is negative 5. So to find the inverse, we will have the inverse of the coefficient matrix, 1 over negative 5 times the mixed up matrix. Flip these two, the other two change signs. So now when we carry out our multiplication to get that inverse, we're going to have negative 1, negative 3/5, negative 1, and negative 2/5. Now remember, in order to solve for that unknown matrix, what we need to do is A inverse B. We need to multiply it by that resultant matrix. The resultant matrix was negative 120. Now again, I want you to think about the sizes. This is a 2 by 2 matrix, and this is a 2 by 1 matrix. So our result is going to be another 2 by 1 matrix. We're going to be finding x and y. So when we carry out our multiplication, we have row 1, column 1. We're going to end up with 1, and then plus negative 65ths. And then for the second term, we're going to have row 2, column 1, 1 plus negative 45ths. Now before I just left them in fractional form, I said, well, I use my calculator. But here you can really easily figure out what these two things are, because this is just going to be 1 minus 12, which is negative 11. And this one is just going to be 1 minus 8, which is negative 7. So we can see that at the end of the day, x equals negative 11 and y equals negative 7. This one was a little bit faster. Those fractions were a little bit nicer to deal with. This example is a little bit different. It's already set up as a matrix equation for us. But what we have here is something like ax plus c equals b. And in order to solve this, I need to just have ax equal a single matrix. So before we can do anything else, we're going to need to move matrix C to the other side of the equation. So that means we're subtracting that matrix from both sides. We can do this because they're the same size matrices. Now, if you remember from subtracting matrices, all that means is that you are subtracting the corresponding terms. So we will end up with 23 minus 3, which is 20. And we will have negative 3 minus 0, which is, I'm going to draw this line to help you see that a little bit better, negative 3. And we have 13 minus negative 2, which is 15. We're going to have 2 minus 5, which is negative 3. So that's our new B, or our new resulting matrix. We started out with negative 6, negative 5, negative 5, negative 4 times some unknown matrix X. Now let's think about what we're actually going to do here. We're going to do A inverse B. We're going to find the inverse of this matrix. We're going to multiply it by that matrix. So we are going to have a 2 by 2 matrix. We're going to multiply it by another 2 by 2 matrix. So how big is matrix X going to be? Well, remember, those two match, and we're going to have a 2 by 2 matrix. So that's what we're going to be solving for. First, though, we have to find the inverse of this one. Remember, it's 1 over the determinant times the mixed up matrix. So the determinant is going to be, I'll put this over here, positive 24 minus positive 25, which is negative 1. Yay, we like it when the determinant is negative 1, because here's what that means. 1 over negative 1 times the mixed up matrix. So you flip these two, change the signs of the other two, and we multiply. So negative 1 times negative 4 will get me 4, negative 5, and 6. Now, that's A inverse, and we're going to multiply it by B, which is that resulting matrix. And so we are going to carry out the multiplication between 2 by 2 matrices. And we know that our final product, or our final solution, is going to be another 2 by 2 matrix. We already decided that. So it's just a matter of row 1, column 1, and so on and so forth. So row 1, column 1 is going to be 80 minus 5 times, well, negative 5 times 15 is negative 75. So we have minus 75, so that part is going to get me a 5. Then we're going to have row 1, column 2, and that will get us negative 12 plus 15, because it's positive 15, so that'll give us 3. Now we have row 2, column 1. That's going to get me negative 100 plus 6 times 5, which is 90. So we have a negative 10. And last but not least, row 2, column 2 will get me 15 plus negative 18. So that one's negative 3. So in this case, we weren't solving for a variable or a particular variable. We were solving for a variable matrix, which meant an unknown matrix. And there's our unknown matrix, 5, 3, negative 10, and negative 3. For the rest of the examples in this video, I'm going to focus on setting up the matrix equation, and then we're going to use technology in order to solve it. So again, I said you could use handheld calculators to find inverses, and you can also use a lot of calculators online. I'll make sure that those are on the Canvas page. The trickiest part of these is setting it up. Once you have it set up, it's pretty easy to make the matrix equation. And then if you're using technology, it becomes even easier to find the solution. So, 2 small pitchers and 1 large pitcher can hold 8 cups. And 1 large pitcher minus 1 small pitcher can hold 2 cups. How many cups of water can each pitcher hold? Alright, well the first thing we need to do is determine what our variables are. I'm going to let large equal the large, or L equal the large ones. And I'm going to use, I guess we'll use S. I hate S, but there's my S for the small ones. Now, I know that 2 smalls plus 1 large holds 8 cups. So 2 small plus 1 large equals 8. And I know that 1 large minus 1 small is 2. So we have a system here. Now before we can set it up in our matrix equation, we need to make sure that our variables are all in the same order. It's really important because when you think about matrix multiplication and you're multiplying it by a variable matrix, you need to make sure that the first term is going with the same variable in both equations. So these are actually not good as they are. I'm going to switch this first one around. That way I have large plus 2 smalls equals 8. And that's the system I'm going to set up. Do you see how the larges all match up, the smalls all match up, and then the results all match up? That's what we would do if we were solving using elimination too. So it's something that you're already familiar with. So let's set up our matrix equation. 1 large minus 1 small, 1 large plus 2 smalls, times large, small, equals 2 and 8. Something that's cool about matrix equations is that if you wrote them in a different order, if you wrote the 2 equations in a different order, that's absolutely fine. As long as everything in the first row is of one equation and everything in the second rows is of the other equation, we're good. So I know when I actually practiced solving this one, I actually did it in the other order, but we're going to get the same solution. As long as we have the order of our variables right, we'll be able to tell which is which. So I'm going to call this matrix A, that's matrix X, and that's matrix B. In order to solve this matrix equation, I know at the end of the day I'm going to have X equals the inverse of A times B. So this is where I told you we're going to use technology. I actually could find the inverse of this and do it like I did the other problems by hand. However, we have stuff that'll do it for us. Let's utilize that. So whether you're using an online calculator or whether you're using a handheld graphing calculator, the first thing you need to do is find the inverse of A and then multiply it by B. Depending on the calculator you're using, some of them would do this all in one fell swoop for you. Handheld calculators will. If you're using an online one, you might not find one that will do both terms for you or both operations for you. So you might have to find the inverse of A first. After you find that, plug that matrix in and multiply it by matrix B. Either way, no matter what you do, you're going to end up with a matrix, and it will give you a matrix that looks like a 2 by 2 matrix. And when I did this, I ended up with 4 large and 2 small, or I ended up with that matrix as my solution. Since the original setup that I had large in the top entry, that means that large is 4 cups of water. And small is 2 cups of water. Because large was in the top place and small was in the bottom place. If you would have done your variables different, your equation would have looked different and your result might have been 2 over 4, but you would have known what was what because you set up the matrix equation. Alright, so we have a theater that has tickets that are $6 for adults, $3.50 for students, and $2.50 for children. A total of 278 tickets were sold for one showing with a revenue of $1,300. If the number of adult tickets was 10 less than twice the number of the student tickets, how many of each type was sold? So let's think about our variables in this case. It says how many of each type. So my types are what I'm looking for. I need to know how many adult tickets were there. So I'm going to use A to be adults. I need to know how many student tickets there were. I'm going to use T for student because I hate those S's. And we need to know how many children were there. So I'm going to let C be the child tickets. This one's different because it has 3 variables in it. We haven't done a lot with 3 variables. Mostly we've just been looking at 2. So here's an example of where you're going to want to use matrices. You don't want to do this one by hand. Let's go ahead and set up our equations. Since we have 3 variables, that means we need 3 equations. So let's see if we can find them. We know that we make $6 for every adult, and we know that we're also going to make $3.50 for every student, and we're going to make $2.50 for every child. And when you do this multiplication, you're going to get your total amount of money you made, which in this case was $1,300. Alright, well I also know that I sold a total of 278 tickets. Okay, well that means the number of adult tickets plus the number of student tickets plus the number of children's tickets was 278. Now the last statement that's going to help me out and find my third equation says the number of adult tickets was 10 less than twice the number of student tickets. Alright, I have my 3 equations. We're not quite ready to go ahead and make our matrix though, because even though these first 2 equations are all lined up like they're supposed to, the third one is not. So what we're going to need to do is move that t over, move those t's over, so that we now have an equation that says a minus 2t equals negative 10. So that's what we're going to be looking at. These are our 3 equations that we're going to use to write our matrices. So let's go ahead and do that now. Since everything's in the right order, I see that I have 6, 3.5, and 2.5 as my coefficients in the first matrix. Now, this order that I determined was that it was going to be A, and then T, and then C. So my variable matrix needs to be in that order too. Now for the second, I'll go ahead and do the result while we're thinking about it. This was 1,300. Now for the second equation, we had 1, 1, and 1 as our coefficients, and that equaled 278. Now for our third equation, we had 1 adult, negative 2 students, and no children. So you need to make sure you fill in that entry in your matrix. You need to put a 0 there. And it equaled negative 10. So if you look at the matrices that you have now, you have a 3 by 3 matrix, let's call that A. Then you have a 3 by 1 matrix, let's call that X. And you have another 3 by 1 matrix, and let's call that B. So using your calculator, you're going to do A inverse B. This is a good one because we're finding matrices of 3 by 3 matrices. We're not finding inverses of 3 by 3 matrices by hand. So we couldn't do this one by hand. We would need to rely on a calculator either online or in your hand. So when you actually perform that operation, A inverse B, what you're going to end up with is a 3 by 3 matrix. And your 3 by 3 matrix, if you did all your work right, it's going to be 150, 80, and 48. But now you have to interpret what that matrix means. You can't just leave it like that. It doesn't really tell us very much information. So I would say that I sold 150 adult tickets. And I sold 80 student tickets, because that's the order they're in. And I also sold 48 child tickets. Alright, the measure of the largest angle of a triangle is 10 more than the measures of the other 2 angles, and 10 less than 3 times the measure of the smallest angle. I want to find the measures of the three angles. So obviously I have three things going on here. This is a triangle. It has three angles in it. We know that much. So the first thing we need to do is think about what we're finding and to define our variables. We want to find the three angles. Well, since it's talking about large and small and all that, I'm going to let L equal the measure of the largest. And then I'll let M be the medium or the middle. And I am going to use S to be the smallest angle. Now, we have three variables. We have three angles we're trying to find. If we had a problem about a quadrilateral, we'd have to find four angles. But in this case, we just have three, so we need three equations. I'm going to start out with the first piece of information that I was given. It says that the largest angle is 10 more than the other two angles. So the largest angle is the medium and the smaller one, and 10. Okay? Then it also says that that large angle is 10 degrees less than 3 times the measure of the smallest angle. So the large is 10 less than 3 times the small. And that's it. That's all I'm given. But I only have two equations. Okay, well, think about what you know about a triangle. The large angle plus the middle angle plus the smallest angle has to equal 180. So our third equation comes from that. Large plus medium plus small equals 180. And those are my three equations. Now, I didn't write them down on top of each other yet because I noticed that I'm going to need to do some changing. I'm going to need to get all of the variables together. And it doesn't matter what order you have the variables in as long as you're consistent. Since this one's already in a good form, I'm going to leave it like that, large, medium, small. So I'm going to need to convert the other two. In this one, the first one, I am going to move the medium and the small over to the other side with the large. So that way I end up with large minus medium minus small equals 10, because those cancel. I'm also going to change the middle equation. I think I'm going to just move the 3 small over. So I'm going to have large minus 3 smalls equals negative 10. And then I also have the large plus the medium plus the small, which equals 180. Now, while we're in here in this form, before we make our matrix equation, let's look at the second equation. It doesn't have any mediums. So if it helps you, go ahead and fill in 0 mediums. That way we know what our coefficient is going to be. Because now it's just a matter of setting up our variable matrix and our coefficient matrix, and our result matrix. So the variable matrix, I have 3 variables, so I know I'm going to have large, medium, and small. The result matrix is going to be 10, negative 10, and 180. And then let's go ahead and fill in those coefficients. Large is 1, minus 1, minus 1. 1, 0, negative 3, 1, 1, 1. Now this is another one where when I did this previously, I set it up in a different order. I had the last equation written first, and that just meant that I changed where my result matrix entries were. But again, as long as you're consistent, you're good. So at this point, this is where we want to go ahead and do A inverse B, and that's going to get us our missing matrix X. And again, since this is a 3 by 3 matrix, what we want to do is rely on our technology in order to solve that for us. And when we do that, we should end up with a 3 by 1 matrix. So when I did that, I got a 3 by 1 matrix that was 95, 50, and 35. Again, we need to interpret this. What does this actually mean? Well, it means that the largest angle was 95 degrees. The medium angle was 50 degrees, and the smallest angle was 35 degrees. Now here's where you can use your smarts in order to make sure you did this right. You can look at that and go, okay, are they in the right order? Is the biggest angle really the one with the highest degree? And do I really have the lowest degree with the smallest angle? In this case we do, so we did good. Now, another time that I've done this problem, I forgot something in my equation. So when I set up my matrices, I was missing one entry that was a little bit different. And I got some kind of crazy answers in my matrix. So that's another thing you can think about. If you're getting some stuff that doesn't make sense, go back and look at your equations again. See what you're missing, and you might need to reevaluate that A inverse B. So, a rectangular garden has a 20-foot perimeter. And the length of our garden is 4 feet more than the width. Find the dimensions. How many dimensions does a rectangle have? 2. So this is a 2-variable equation. We're going to have length and width. And so we're only going to have 2 equations in this situation. So it says the garden has a 20-foot perimeter. Well, that means I know that twice the length plus twice the width is equal to 20. It also says that the length is 4 more than the width. So I have my 2 equations. If I want to solve this using matrices, I need to get them change the order. If I were going to solve using substitution, I would probably use how they are right now. Since we're practicing matrices, we're going to go ahead and change the second equation. That way, I have length minus the width equals 4. Now, since this is 2 variables, 2 equations, I'm ready to set up my matrix equation. We only have the 2 variables, and the order that they're written in is L first and then W, so that's how I'm filling in my matrix. And so this means we're only going to have a 2 by 2 matrix. So coefficients and results or constants, we're ready to go. So remember, we're going to use our technology this time, and we are going to find A inverse times B. It's really important for you to remember to do both steps. Find the inverse of A, and then multiply it by B. Remember, multiplying matrices, the order matters, so you have to do A inverse, then times B. You can't switch it around. When you do this, you are going to end up with X equaling a 2 by 2 matrix. And in this case, our matrix is going to be 7 and 3. So let's think about what this actually means in terms of the problem. Since L was on top, that means that L is 7. So the length is 7 feet. And the width is 3 feet. And again, check yourself. Does it make sense that the width is 3 feet? Well, yeah, since the length is 4 more than that, 7 is 4 more than 3, so I'm feeling pretty confident about our answer. The results of a chili cook-off are shown below. How many points are first, second, and third place votes worth? Alright, so we have a table this time, and we need to set up some equations. Believe it or not, these are actually my favorite type because the matrices are secretly already done for you. Let's think about this. We have Jada. She gets 3 first place votes. So 3 times the number of first place votes she gets is how many points she got from that. And for second place, it would just be 1 times however many points that one is worth. And for third place, it would be 4 times however many points that one's worth. Altogether, it's going to get her total points of 15. Since the table is already set up, first, second, third, I decided to use X, Y, and Z as my 3 variables. Doesn't matter what you use as long as you remember what they are. Now you can kind of see how the rest of the equations are going to go. Maria, she got 2 votes times the number of points, plus 4 votes times the number of points, plus no votes times the number of points, and she ended up with 14 points. So that was her result. Then we had Al, and Al got 2 votes times the number of points, plus 2 votes times the number of points, plus 3 votes times the number of points, and he ended up with 13. So we can see that Jada won, or Jada, I'm not sure how you would say it. She won, but we need to know how many points each of those votes are worth. So we actually have a nice little system already set up. Everything's in the right order. All the X's are together, all the Y's are together, all the Z's are together, and all the results are together. So you can see how this translates from the table into my equations pretty easy. You can also kind of get to the matrices pretty quickly too. we're thinking about coefficients, I have 3, 1, and 4, 2, 4, and 0, and 2, 2, and 3. Then we have our variable matrix, and I chose to use x, y, and z. I'm putting them in this order because, remember, think about matrix multiplication. Row 1, column 1, that would be 3 times x, 1 times y, and 4 times z. That's going to get us our result matrix, which is 15, 14, and 13. So this is matrix A, that's matrix X, and this is matrix B. So we can use our technology to find A inverse B, and we should be able to find the number of points that we get. And our matrix that we get, matrix X, is going to be a 3 by 1 matrix. So in this case, when you do this, you end up with X equals a 3 by 1 matrix, which is 3, 2, 1. And remember that matrix is not your final answer in this case. We have to actually say what's what. So in this case, we know that our first place vote is worth 3 points because that's what X represented, the number of points for first place. And a second place vote is worth 2 points because that's what Y represented. And a third place vote is worth 1 point. So there we have our solution to that big, giant system of equations relatively quickly when we were able to use matrices. Right, I have one more I want to set up because setting up the systems is the trickiest part. Once you get them into your matrices, you're pretty much good to go. But we want to make sure we're setting them up correctly. So we have Ryan, Tammy, and John, and they drive a total of 50 miles to work each day. Now Tammy drives twice as far as Ryan, and John drives 10 miles farther than Tammy. So how far does each person drive? Well, I have 3 people, so I need 3 variables. So I'm going to choose to use R for Ryan, and T for Tammy, and J for John, because those are all nice ones. Now I know that all together they drive a total of 50 miles. So Ryan plus Tammy plus John is 50 miles. I also know that Tammy is twice the distance that Ryan goes. And I know that John is 10 farther than Tammy. So for my 3 variables, I have 3 equations. This is a good thing. However, they're not all in the right setup for me to use a matrix to do this. Now, I could use substitution or elimination if I wanted to. I probably would want to, but I know that you guys would probably want to use a matrix instead. So we need to alter our equations a little bit. This first one is already in a nice order. R, T, J, everything's in the right place. So I'm going to use that as my model. So for the Tammy equation, I'm going to move the 2 R's over. So I'm going to have Tammy and minus 2 Ryans, no Johns, equals, well, what do you have left if you have 2R and you take away 2R? You don't have anything left. And how do we represent nothing in math? 0. So we do have a result on that side. You need to make sure you fill that in. Now let's look at the last equation. I'm going to move Tammy over. So I have no Ryans. I have a minus Tammy. And I have 1 John. And that equals 10. So I have my system already set up. All the Ryans are in the same place. All the Tammys are in the same place. All the Johns are in the same place. All the results are in the same place. So we can go ahead and write this as matrices. Coefficient matrix, variable matrix, and result matrix or constant matrix. So since we have 3 variables, and the order I have them written in is Ryan, Tammy, John, that's the order I need to write them in my variable matrix. So we have 1 Ryan, 1 Tammy, and 1 John, and they equal 50. Second equation, minus 2 Ryans, 1 Tammy, no Johns, and they equal 0. Needs to be included. That matrix needs to be 3 by 1. And then we have no Ryans, negative 1 Tammy, and 1 John, and that gets us 10. So we have our setup ready to go. We have matrix A, we have matrix X, and we have matrix B. So we're going to use our technology to find A inverse times B. And when we do that, we should get a 3 by 1 matrix as our result. So when I do it on my calculator, I get 8, 16, and 26. And again, let's interpret these things. Let's figure out what they actually mean. Ryan was in the top spot, so Ryan is 8. He drives 8 miles. Tammy was in the second spot, so Tammy is 16. Tammy drives 16 miles. And John was in the last spot, so John drives 26 miles. Now think about that. Think about this situation. It says Tammy drives twice as far as Ryan. Yeah, 16 is twice 8. And it says John drives 10 farther than Tammy. And 16 plus 10 is 26. So I can feel pretty confident about the solutions that came out when I did A inverse B calculation with my calculator. So getting on to our recap, solving systems using matrices requires us to convert a system into matrices. So usually what you do is you get them into standard form so that everything is lined up. And then you end up making 3 matrices. The first one is the coefficient matrix. So you put all the coefficients in there. The second one is the variable matrix. That's where the variables go, and you make sure you have them in the right order from standard form. And that is the result matrix, or sometimes I call it the constant matrix. That's where you put everything that's on the other side of the equal sign. And then you're going to carry out your calculations, because remember, we're trying to solve x. And normally we'd say, oh, you divide by a, but we don't divide by matrices, so we have to show what divided by is, and that means multiplying by the inverse. So you multiply both sides by the inverse of a. That becomes an identity matrix, so they cancel out. You're left with the matrix X equals A inverse B. For 2 by 2 matrices, we know how to find the inverse of A, and so we can go ahead and solve that by hand. For larger matrices, we can't do it by hand, so we rely on technology. Depending on what you're using, you might be able to just type in the matrix A, type in matrix B, and then carry out the command A inverse times B. If you're using something else, some of the online calculators, you might have to find the inverse of A, store that for later, and then input B, and then find the product. So make sure you're careful, depending on the calculator you're using, to make sure you're doing the correct thing. And remember, when you get your answer, you're going to end up with a matrix. So matrix X might be a 3 by 1 matrix. We saw lots of those. And if you're just solving a generic matrix setup equation, yeah, you want a matrix as your final answer. However, if you're solving a system, remember we usually write our systems as an ordered pair or an ordered triplet. Or if it's a word problem, you want to define what the answers mean. Not only is this good practice, but it is also something that will help you think about your solutions and make sure you did it right. Because the tricky thing about using technology in order to solve these is that if you type in one number wrong, everything goes awry. So make sure you're being really careful and not relying on that too much. So that was solving systems with matrices, one of the awesome things we can do with matrices, but just one of the few awesome things that matrices can do for us.